Hello, everyone. I'm Andy Farhadureza. I'm an associate professor of computer science at Eastern Illinois University. My undergraduate student Dominic Cloud worked with me on this paper where we are using neural networks for mapping deep neural networks onto network-on-chip architectures. We know deep neural networks is very popular, used in many applications. It has computation and also communication. Communication can be global or local in the convolution layers, global in the fully connected layers. The network on chip is standard communication fabric, which is scalable and parallel communication communication fabric for multi or many core systems. Um, but it is also challenged by the during communication patterns because we know the communication is a major challenge because during communication we are not doing any useful work. And in large scale systems, we can spend more than 50% of the time for communication. Um, and which hampers our computational parallelism because computation needs the data that is sent by the communication. And also communication is more time, significantly more energy consuming because intercore data transmission can be 224 times the more energy consumption compared to the intracore one. And also with the more increase in the DNN sizes, more intercore connections are needed, making intercore communication a significant challenge on the NOx. And we know, and as we talked about that, communication is dominating the chip power because of the is more energy consuming. And we can, in our problem statement, we can say that mapping DNA neurons to cores is our main objective. And we know that this is an NP-hard problem similar to the bin packing, but it has more dimension. For example, we need to take care of the communication latency. We need to balance the computational load. We need to respect the capacity constraints of the cores and links and routers. And you know that traditional heuristics, they might give us the solution, but they are very slow and they may not generalize well to the many different DNNs because of their different communication patterns. And neural network solutions, we are using 9-dimensional feature vector, and each of them contributing something. For example, mean of incoming weights guides the placement of the important neurons. Bias term is for grouping the frequently active neurons together. And normalized global index maintains the execution order of the core. In the neural mapper solution, we are using the 3-layer feed-forward networks, including input layer, which will be 4 layers. And our output of these neural networks is the probability distributions of the cores. So for each neuron, if there are 64 cores, there will be 64 probabilities. But this probability will be discrete, and discrete will not be differentiable. So for gradient learning, we are injecting the noise gumball and to make the gumball subnoise to make it differentiable. And temperature parameter addresses the exploration and exploitation. During the initial time, we are going to do the more exploration, so tau will be a higher value. But with the time goes on, we are going to reduce the flickering of the cores to the neurons to the different cores. We're going to reduce that, so tau will be reduced. And it's called this probability distribution value is called, we say, the logit score, and we are using that in our formulas. So in a loss function for our training, we are using communication cost as a penalizing. So if there are more communication, that will be more distances, more Manhattan distances, that will penalize our model so that it can learn better. And also if there is a higher deviation between the core loads, and that will also penalize our training loss function. And capacity penalty, if any mapping increases the load more than the capacity of the core, that will also be one penalty for our loss function. And And also, we want to avoid the maximum load penalty. We discourage in the course from exceeding the double of the mean load. This helps our learning all these cost losses in our training of the neural networks. We are using AdamW optimizer because it provides more stability. And during inferences, actually, even though during training time, the linear mapping will exceed the capacity constraint of the course, but during inference time, we're going to apply validation so that no core exceeds the capacity in the during final mapping. Um, and output will be the valid one hot neuron to core mapping. And simulation, we use 16 to 256 scores. We use the CIFAR10 and Fashion MNIST dataset. We use them for our creating our DNNs. So we use the in-house developed mapper and the solutions from our mapper. We send that to the Gem5 and Garnet and this for latency throughput analysis. And this set we use for energy consumption. And we can see that is significant training in the training loss or our maximum core load. We see that it significantly decreases in initial epochs. And so maximum core load reduced by 6.5 times in fashion MNIST and 6.1 times in the CIFAR10. And loss also drops sharply in the first few epochs. So that means we are learning very early in our during our training. And it is expected that because neural networks can give during the inference, it can give the solutions very instantly. So it will be significantly faster in that 13,000 times faster than the heuristics. And GA genetic algorithm is the slowest due to these populations evaluations, the number of mappings evaluations it needs to do, and simulated annealing is the fastest among the heuristics. Um, and performance scores, neural networks outperforms the heuristics, and in fashion MNIST is 17.1% better than the GA, and CIFAR10 it is 13.6 times better than the genetic algorithm. And so simulated annealing again performs close to the neural networks in many cases. Um, so in a Gen5 or Garnet evaluation, we see the neural networks reduces latency by 2 to 6%. Throughput is always competitively. Sometimes similarly, annealing can also give the better performance, better throughput compared to our neural networks. We can see the similar pattern in the fashion MNIST DNNs. And for energy consumption, we saw the neural network saves up to 5.2% energy compared to heuristics, and performance is consistent across the 16 core and 64 core nodes. And Similar thing for fashion and NIST DNNs. So overall, we can see that neural networks is a constant time inference. So it is very faster. It is can generalize better, works with unseen DNN logs. It balances the load distribution, communication efficiency, it reduces communication volume, and it consider the capacity constraint of the systems. And it can also aware about the hardware awareness, capacity, again related to the capacity constraints, and uh, and also uses the different features to capture the neuron characteristics. And limitation is that it needs more training, and sometimes heuristics performs better. So overall, yes, we can say that neural network based mapper is suitable for real time and large scale DNN and now deployments. Thank you.